Hey everyone, and welcome. Today, we're diving into something that might sound a little scary, but it's actually one of the most powerful tools ever invented for making sense of our world: trigonometry. And forget about dusty old textbooks, because we're going to see how this thing lets us measure stuff we could never, ever reach with a tape measure. We're talking about the height of a mountain or even the distance to a star. So here's the game plan for the next few minutes. First, we're going to tackle this huge idea of measuring the impossible. Then we'll unlock the secret code that makes it all click. After that, we'll test out our new skills, apply them to some real-world problems, and hopefully you'll see how this gives us a totally new way of looking at everything around us. Sound ready? Let's jump in.
All right, first things first. Before we get into the how, we really need to get the why. What was the huge fundamental problem that made someone, centuries ago, even invent trigonometry in the first place? No, really, just think about that for a second. How would you figure out the exact height of a mountain without actually climbing it with a giant ruler? Or how high up is that kite really? For hundreds of years, this was a massive headache for pretty much everyone. Surveyors, astronomers, you name it. You can't just walk up and measure it. And that is the problem trigonometry was born to solve. It's the math of measuring things from a distance. Okay, so if we can't measure directly, what do? Well, the answer is kind of like a secret code, one that's hidden in plain sight inside one of the simplest shapes you can imagine. And this is it. This is the hero of our story, the humble right-angled triangle. It turns out this one simple shape has these incredibly predictable, consistent rules that we can totally use to measure just about anything. Now, this part is absolutely key, so stick with me. How we name the sides of this triangle depends completely on which angle we're looking from. So let's say we're standing at angle A. The side way over on the other side of the triangle from it, that's the opposite. The side right next to it, the one helping to form the angle, that's the adjacent. And that long slanted side, the one across from the right angle, that one's always called the hypotenuse. Getting these three names down is everything. Okay, so tool number one in our new toolkit is sine, which we just write as sin. All sine is a fancy name for a very specific comparison or ratio. It's the length of the opposite side divided by the length of the hypotenuse. Now, here is the magic part. For any angle you pick, let's say 30 degrees, that ratio is always the same. I don't care if the triangle is tiny or as big as a building. If the angle is 30 degrees, that ratio is a constant. That predictability is its superpower. All right, next up is cosine, or cos. And don't worry, it works the exact same way, it just uses a different pair of sides. This time, it's the length of the adjacent side divided by the length of the hypotenuse. And just like sine, for any given angle, this ratio is always the same fixed, predictable number. And the last piece of our toolkit is tangent, or tan. This one compares the opposite side to the adjacent side. And that's it. These three relationships, sine, cosine, and tangent, that's the whole foundation. This is the complete toolkit we need to start measuring the world. Okay, so how on earth are you supposed to remember all that? Well, there's a secret code. SOHCAHTOA. To say it out loud, SOHCAHTOA. S, sine, is opposite over hypotenuse. C, cosine, is adjacent over hypotenuse. And T, tangent, is opposite over adjacent. SOHCAHTOA. Seriously, burn that into your brain. It is the key that unlocks everything. Okay, we've got the code, we've got the tools, SOHCAHTOA, so now it's time to actually use it. Before we go and try to measure a real mountain, let's hit the training ground with a pure math puzzle just to make sure we've got the moves down. So here's our first challenge. Let's say we have some angle, we'll just call it A. Now, we don't know how many degrees it is, but we do know one thing about it. Its sine is 3/4. Our mission is to figure out the cosine and the tangent for that exact same angle using only that one little clue. Right, so first things first, let's turn this number thing back into a picture, into a triangle. Remember SOHCAHTOA? So tells us that sine is opposite over hypotenuse. So if sine of A is 3/4, we can sketch a triangle where the opposite side is 3 units long and the hypotenuse is 4 units long. Now, it could also be 6 and 8 or 30 and 40. So to cover all the bases, we'll just call the sides 3K and 4K. Now, there's just one piece missing, that adjacent side. We got to find it. So how do we find the third side of a right triangle when we already know two of them? Well, for that, we call in an old friend, the Pythagorean theorem. You know, a squared plus b squared equals c squared. We plug in our numbers, do a little bit of algebra, and we find out our missing adjacent side is the square root of 7.
times k. So now we have all three sides. The opposite is 3k, the adjacent is root 7k, and the hypotenuse is 4k. From here, it's easy. We just use SOHCAHTOA again. Cosine is adjacent over hypotenuse, which is root 7 over 4. Tangent is opposite over adjacent, which is 3 over root 7. And just like that, puzzle solved. Awesome. So we've nailed the theory. But now for the fun part, the real payoff. Let's take these skills out of the notebook and actually use them to measure the world around us. Okay, first real-world problem. Get this picture in your head. There's a circus artist, and she's climbing a vertical pole. A rope is stretched from the very top of that pole all the way down to a point on the ground. That rope is 20 meters long, and where it hits the ground, it makes a 30-degree angle. So the question is, just how high is that pole? Let's break this down into a triangle. From the point of view of our 30-degree angle, the pole is the opposite side. It's the height we want to find. The rope, that's the long slanted side, so it's our hypotenuse. So what do we have? We have opposite and hypotenuse. Quick, check the code, SOHCAHTOA. Which one uses O and H? So we got to use sine. So we just set up the equation. The sine of 30 degrees equals the height, our opposite, divided by 20, our hypotenuse. You can punch sine of 30 into any calculator, do one quick step of multiplication, and bam, the height of the pole is exactly 10 meters. Now think about that for a second. We just measured the height of that pole without a ladder, without climbing it, just by standing on the ground with a little bit of math. All right, you ready for another one? Let's do it. A kite is flying straight up, and it's 60 meters off the ground. The string is pulled tight, and it makes a 60-degree angle with the ground. The question is, how much string have you let out? Okay, let's break it down again. This time, we know the opposite side, that's the height, 60 meters. And we want to find the hypotenuse, that's the length of the string. So again, it's opposite and hypotenuse, which means we're using sine. Sine of 60 degrees equals 60 divided by our string length. We just rearrange that equation, solve for the string, and we find out it's 40 times the square root of 3 meters long. And boom, just like that, another measurement that seemed impossible is now just a simple number. So, we've cracked SOHCAHTOA, we've solved some real-world puzzles, but what's the big picture here? What should you really take away from all of this? Here's the most important thing to remember. Trigonometry basically gives us a superpower. It lets us see the invisible relationships between angles and distances. Because we know that those simple ratios in a right-angled triangle, our SOHCAHTOA, are always constant and predictable. We can model the world around us. We can take a massive, complicated, unreachable problem, and we can shrink it down into a simple triangle that we can solve on a piece of paper. It turns the impossible into just a simple calculation. And that is the real magic. Because once you get this, you start to see the world in a totally different way. That tall tree in the park, the skyscraper downtown, even the clouds in the sky, they all become part of these potential puzzles you can solve. So I'll leave you with this question. Look around you right now. What puzzles in your world could you solve?